Okay, we're still considering the topic hydrocarbons. We have talked about alkanes. Now we are getting into alkenes. Now, the alkenes are a homologous series of hydrocarbons with a general molecular formula of CnH2n. Remember, alkane was CnH2n plus 2. So alkene now is CnH2n, so there is no plus 2, which means that alkenes have 2 hydrogen shots of the alkane, so has 2 hydrogen less than its corresponding alkane. Good. So the formula is CnH2n, where n is a positive whole number which is equal or greater than 2. So the least is 2. So in alkenes, you must the least is the smallest member is going to have 2 carbon atoms. So it's not going to be like met. There is no met because met means 1 carbon atom. But in alkenes, the smallest member has 2 carbon atoms. So the first member has to be ethane, 2. All right. And you know that alkenes have double bond. Alkanes have single bond. Alkenes have double bond. And alkynes have triple bonds. We've handled the single bonds, the alkanes, and we said they are saturated. Once they have single bonds, they are saturated. Now we are getting into the unsaturated ones now, the alkenes and the alkynes, and we are considering alkenes. If alkenes have double bond, there is no double bond between carbon and hydrogen. Hydrogen has only 1 electron, so it can only share 1 bond. But because of that, carbon can only have double bond with carbon in hydrocarbons. So because for you to have 1 double bond, you need 2 carbon atoms. Alright, so because of that, that's why the simplest member has to be C2. It has 2 carbon atoms. So that's why hydrogen is 2 less, because the double bond, remember the other time, double bond has taken the place for 2 hydrogen and bonded it with carbon. Alright, so ethane is the first member of the alkene series. Ethene. Remember, we're not saying ethane now. Ethane is for alkane. Ethene now is for alkene. Good, remember. Now, so ethene, propene, but 1 in and but 2 in. But 1 in and but 2 in are isomers of butane. We'll get to know that as we proceed. So ethene, propene, but 1 in and but 2 in are colorless gases at ordinary temperatures and pressures. But the others, the next 13 members, are liquids, while from the ones higher than the next 13 members, as the one from C18 above, they are all solids. So alkenes burn with a more luminous and smoky flames than the corresponding alkanes. We say all hydrocarbons burn in air to produce water and carbon dioxide. But now alkenes burn with more smoke than the alkanes. The reason is that if you take only one, the first member of the alkane series, methane, CH4, has 1 carbon atom and 4 hydrogen atoms, right? Good. Now let's see the first member of the alkene series has 2 carbon atoms and how many hydrogen atoms? 4 hydrogen atoms. Remember, the other one had only 1 carbon atom, but still 4 hydrogen atoms. This one, the first member, has 2 carbon atoms, but 4 hydrogen atoms, which means hydrogen did not change, but carbon increased here. The more the carbon, the more the smoke. Just like the more the firewood in your fire, the more the smoke, understand? So, because of the carbon has increased now, there's more carbon in these alkenes than there is carbon in alkanes. And so it burns more smoky. And all that. So now whenever you see double bonds, it means unsaturation, double bond and triple bonds. It means unsaturation. Single bonds are saturation, saturated compounds. You know that already. But in unsaturated compounds or hydrocarbons, the double bond shows they are more reactive. They're going to be more reactive. So alkanes have single bond. They are not as reactive as the double bonds. So double bond is more reactive because it has double bond. Alkenes are more reactive because they have double bonds, and alkynes are even more reactive than alkenes because they have triple bonds. So double bonds in alkenes make alkenes more chemically more reactive than the alkanes. And if you see the table there, you see the first member ethene, second member propene, third member butene, and so on. Just see that table and see after 9 we should be 10 for alkane, decane. Now decene here, the 10th member will now be dodecane, like 11. You understand? I studied that table. It's just almost the same thing as the alkane table, but just check the formula there. The formula of ethene is C2H4, propene C3H6. So you see they still differ by CH2. They just keep adding 1C and 2H. The other one was C2H4. The next one added 1C and 2H, C3H6. Next thing like that. That's why we said that all members of the same homologous series differ by the addition of CH2 group. It still stands till now. Now those structures are the structure of that member there. Structure of ethene, CH2 double bond CH2. That's how ethene looks like. If you want to draw it, you will see how it is. Propene, the same way. Just study that table and you understand better. Now, what are the rules for naming alkenes and alkynes? Take notes. We are going to be doing rules for naming alkenes and alkynes, but we've not done alkynes yet. The reason why I mentioned that is that this rule will be the same for all unsaturated compounds. They are not saturated like alkanes, so they have one thing in common, that they are unsaturated, double bond, triple bond. So we can blend that together and set up a rule for them, so that we'll not need to do rules for naming alkynes when we get to alkynes. They're almost similar. So let's go. Rules for naming alkenes and alkynes. Now, double bonds in hydrocarbons are indicated by replacing the suffix "n" with "in". Remember, suffix comes after the word. So in alkanes, you say methane, you say ethane, you say propane, but all these things you're saying, they all end with "n". Now, when you're coming to compounds that have double bonds, you replace that "n" with "in". That's how we have alkenes. So no more ethane, methane, is ethene, propene, butene, pentene, hexene, and so on, heptene, and all that. So, and if it's triple bond, you will say you will replace the "n" with "ine". So you'll be saying ethyne, propyne, butyne, pentyne, hexyne, heptyne, octyne, nonine, and decyne, and all that. So, but double bonds, you no longer say "n". You replace that suffix "n" with "in". Now, if there is more than one double bond, the suffix is expanded to include a prefix that indicates the number of double bonds present. Since we say "in", one "in" is just "in". Remember, you don't have to say monoine because it's one. It's already one. Remember, when something is one, we don't call one. Except we are saying methane, one carbon atom. That one is necessary. But if you have one double bond, okay, you say ethene or propene or butene, as the case may be. But if it's the structure has two double bonds, you cannot say you cannot keep saying butene, because now it's more than one in the formula. So you have to add the prefix to the in. You remember, in is a suffix. Add a prefix to the in. So you're not going to add it at the end of in. You're adding it before in to show that it's more than one, or it's more than two, or it's more than that. It's one, it's two, or three, or four. So if it's two, you know, die means two, tri means three, tetra, and so on. So if you have two double bonds, it becomes diene. So if it was ethane, propene, we say propene prop 1 diene. You will see how that goes. That one I said is not that it has one in, it's where the functional group, but you will see how it is. But you just discover, you use the prefix di, tri, tetra, and all those to tell how many double bonds you find in that structure. Remember, I said triple bonds are named in a similar way, and you just change the N to ein. Good. Now, in organic chemistry, double and triple bonds are seen as functional groups. That is very important. Remember when we did functional group, you can say hydroxyl group, alcohol group, and all those functional groups. Now, when you see double bond in a structure, in chemistry, that double bond is seen as a functional group. And even it's seniors or other functional groups, because you have to pay more attention to the double bond first before you even think of other functional groups. You'll see how that goes. But double bond and triple bond are seen as functional groups in organic chemistry. Now, let's get to the rules. Number 1, the parent chain is numbered so that the multiple bonds have the lowest numbers. When we say multiple bonds, we're talking about the double bond and the triple bond. So in that structure, first of all, when you want to name your parent chain, remember how we did in the example in alkane, or we can also use the first example in under just after rules for naming alkanes and alkynes. That one that is 1,4-hexadiene. We can use that as a case study as we are doing this. So the parent chain is numbered so that the multiple bonds have lowest numbers, as the double bond and the triple bond have the lowest number, and that means that the double and triple bonds have priority over other subsequent groups, because we are going first for the double and triple bond. We check first for that one. Remember, in alkanes we say you number it so that in a way that the substituent groups, that's the functional groups you have on the straight carbon, will have a lowest number. So we'll be looking at which number of carbon is closest to the first branch. Remember, we're doing that now. That one, we're taking the functional group. We're giving much priority to the functional group. So we go first and check which one is closer to the. But this time, when you have double bond or triple bond in that compound, you go first. You number the straight chain, going first or paying more attention to where the double bond or triple bond is. That is what you think of first. So, like in that example, you see, if we are counting from left to right, you have to count first carbon. That's the one I labeled 6. First carbon, second carbon. That second carbon is where you have a double bond now. That's carbon 5 now. But if you count from right to left, the first carbon already has a double bond. So you have to start your counting from that side. That's from that right. You see, I labeled 1 there. I didn't count from this from left hand side to right hand side. Counted from where the double bond first is closest. You understand? So my parent chain is counted from right to left. 1, 2, 3, 4, 5, 6. Already, you know, since it's 6, it's going to be hexene. That's the parent's chain name, is hexene. You write down that separately and keep. Alright, rule number 2. When both double and triple bonds are present, the double bonds are given the lowest numbers. Remember, if in one compound you have a double bond, which is alkene, and you also have a triple bond, which should be an alkyne, in the same structure. Remember, we said in when you have multiple bonds, you give priority to the multiple bonds before you even think of the subsequent groups. But now, what if the multiple bonds, there is double bond, there is triple bond? Which one do you consider more important? All right, you have to take the double bond first. You have to consider the double bond first. Double bond senior, triple bond here. So when you have double bond and triple bond in the same compound, then you have to give more priority to the double bond. That is, you'll be counting your straight chain, your parent chain, from where the double bond is closest to the boundaries, to the ends where you give the double bond the closest number, the lowest number. All right. If you look at this, the example by the right hand side of the example we are considering, that's that one that is 1,3-hexadiene 5-fine. You will see that we had a chain. That chain has triple bond by the first carbon on your left hand, and the carbon at the end, as by your right, has double bond. So we could have said, and both of them, they are on the first carbon. If we want to consider from left to right, the triple bond is on the first carbon from this side. But if from the other way, double bond is from the first carbon. And we'll not say, which one do you choose first? Remember, you have to give double bond the priority. So that's why I counted from the carbon that had the double bond. So my straight chain started from there and went the other way. So that's rule number 2. Now, rule number 3, when both double bond and triple bonds are present, the N suffix follows the parent chain directly, and the "-ine suffix follows the N suffix. You will see that. The EN suffix, that's supposed to be for the in, but you will not say ENE now. You see how that is used. Follows the parent chain, because you took priority with that directly. And then the "-ine suffix follows the N suffix. So you mention the parent chain, then you put the "-ine" letter. Now notice that the E is left off. I'm not saying "in" now, I'm saying "N." You see how I pronounce that. So we say "N" instead of "in." Now the location of the double bonds is indicated before the parent name, and the location of the triple bonds is indicated before the N and "-ine" suffixes. Now, if you use that example that I just that one that is at the right hand side of the one we are considering, that's that same one that has triple bond and double bond, that 1,3-hexadiene 5-ine. Now, you see that I used that EN there. I didn't say hexadiene 5-ine. Okay, so I just removed the E from the end of hexadiene. It's now called hexadiene 5-ine. Remember the rules. The N suffix follows the parent name. The parent name is hexane. And you have it's hexene, and you have more than one in there, more than one double bond. So it's not just hexene, it's hexa. It should be hexadiene. Di means 2, but since we also have a triple bond in that chain, "-ine," we're not going to complete in that hexadiene. It's going to be hexadiene 5. Now state the double bond, the triple bond now, 5-ine. Triple bond is in the 5th carbon atom. So that's why the name is 1,3-hexadiene 5-ine. That's rule number 3. Now, rule number 4, for a branched unsaturated acyclic, that's acyclic is chain, not cyclic chain. Acyclic is in chain form, it's not cyclic, it's not secular. The parent chain is the longest carbon chain that contains the maximum number of double and triple bonds. Remember the other one, we say we just count in saturated compounds, those ones that are single bonds. You just count the longest chain. Look for the one that is longest. But this one, whatever long chain you are looking for, the parent chain must be the one that has the maximum number of double and triple bond. So if you have a parent chain that has open to the example under the first example, that's the example we are considering is the first example, and the one under it, that one that is very long, 3,4-dipropyl 1,3-hexadiene 5-ine. Now if you look at it, my parents chain are numbered from right to left. 1, 2, 3, 4, 5, 6. Now, let's say we want to find straight chain, and there is no numbering there, and I've not numbered it yet. I can also want to say, from where I numbered 1, I say 1, 2, 3. When you get to 3, you see there is a branch going up. I can say, let's count down and see. Continue from the branch going up. Say 4, 5, 6. It also has 6 carbon atoms, equal to the one I numbered 6 here from this straight horizontal one. I can also say, okay, that should be my parent chain. It's also long. It's also the longest. Okay, I can say that. But when these unsaturated compounds, that's double bond, triple bond compounds, you number straight chain considering the chain that has maximum more double and triple bonds. That is, if I want to number it that way, I'm telling you now, going up from third carbon atom, we'll be having only one double bond. Have you seen that? The double bond on the first carbon, that will be all for my straight chain. All that has become branched chain. So that would not be ideal for unsaturated compounds. But you see, the straight chain I numbered now, the one I numbered in the book, 1, 2, 3, 4, 5, 6, that straight one, has how many double bonds? 2 double bonds and 1 triple bond. So that becomes my parent chain. The rule has changed now. Your parent chain is the one that contains multiple bonds. Try and understand that. Now, but if there are 2 or more chains competing for selection as the parent chain, that is, if you've counted a chain, take for instance, the chain gave you 6 carbon atoms, and those 6 carbon atoms, that 6 carbon atom of your parent chain has 3 multiple bonds, and you see another branch that if you count, it should still give you 6 carbon atoms or even more, but also has 3 multiple bonds. That is, they will be competing for which one you would choose. They all have what it takes for you to choose them as the parent chain. So if you have that kind of situation, you have to choose based on the following clues. 1. The chain with the greatest number of carbon atoms. Remember, if in your structure you have 2 options to choose from, all of them they have three multiple bonds. But now, and the rule says you have to choose from the one that has more multiple bonds. Okay, two of them now have multiple equals number of multiple bonds waiting. So which one do you choose? Now, if you count, which one has more carbon atoms? They may have three multiple bonds, but you discover that one has 8 carbon atoms. The other one has 7 carbon atoms. The one with more carbon atoms will win. That's the one you would choose. But what if they are still equal? There are still 7 carbon atoms, or 8 carbon atoms, 8 carbon atoms each. That's the second clue you're going to use. If all the number of carbon atoms are equal, then the chain containing the maximum number of double bonds is selected. So, when we say multiple bonds, we mean double bond and triple bond. So, if the first option you should choose from has 2 double bonds and 1 triple bond, and the second one has all double bonds, or it has 1 double bond. Okay, let's say the first one had 2 double bonds, 1 triple bond. The second option you may choose from, has 1 double bond, 2 triple bonds. Now, this rule says, since the carbon atoms are still equal also, you have to choose the one that has more double bond. Remember, double bond is senior. It's given priority. So, you choose the one that has more double bond over the other one. And don't ask me if the double bond is still the same. What do you do? It means your village people, they are really looking for your downfall. So, in that case, we pray it doesn't happen. It will not happen in Jesus' name. Okay, so you see that example that we are considering, the first one. The parent chain, that one is the simplest there actually, because it doesn't have any branch. So I just numbered. Remember, double bond is given more priority in unsaturated compounds, in alkenes and alkynes. Double bond is given priority. So I counted from the chain that gives the double bond the lowest number. So my first carbon has to start from the right. So I numbered 1, 2, 3, 4, 5, 6. Now remember we said that double bond is seen as a functional group. So we're going to count where do we find double bonds or multiple bonds. And the only multiple bond we have here, which is the only functional groups actually we have here, is a double bond, and is in two places, the first carbon atom and the fourth carbon atom in my chain there. So since those are the only functional groups, those are the only double bonds we are seeing there, then I'm done naming the compound. So the first carbon atom is where the first double bond came, and the fourth carbon atom is where the second double bond came. So at least there 1, 4. Remember, I use dash to separate numbers from letters. So now my parent chain has 6 carbon atoms, so that should be hexene. But remember, the double bond is more than 1, so I have to add di to show that it's not 1 in, because that in means double bond. Remember, in, E-N-E, means double bond. Y-N-E, ein, means triple bond. A-N-E means single bond. N, so alkanes have single bond. Alkene have double bond. Alkyne has triple bond. So in that structure we have more than 1 in there. We have 2 double bonds, so more two ins. I cannot say hexa 2 in. We say di or tri if there are 2 or 3. So since it's 2, we say diene. So I read that my structure is 1,4-hexadiene. Remember, now I'm saying diene. I'm not saying diene, because there's no alkyne, there's no triple bond in this that I would add at the end. So if there's a triple bond, I will say hexadiene. Now states where the triple bond is. I might say 5-ine. But since this is the only double bond or multiple bonds we have, it ends there. So hexadiene. Good. Now, if you look at the one by just below the example we're just doing right now, you see that in our straight chain, we want to number a straight chain on the carbon that gives the multiple bonds the lowest number. Remember, when I say multiple, I'm talking about double bond or triple bond. Now, if we want to count from left to right, from where I counted 5, we want to count from there, you see that you have to say 1 to the second carbon before you see a double bond. Okay. Now, but if you're counting from where I counted, that's the right to left. On the first carbon, there is a triple bond there. If the triple bond, since there's a triple bond there, we now call that the first carbon. So we have to count from there. It gives the multiple bond the lowest number. So we count it. That's the parent chain. And now when we count that, when we've numbered our parent chain, but there is also a double bond in that structure on the third carbon atom. So remember, in will come before ein because of alphabet. Now remember, alkene, E-N-E, will come before Y-N-E. So we have to, when we are naming that, we have to consider in first before ein. So we have picked out all our functional groups, all our multiple bonds. The first carbon we have triple bond, that's an ein group. We also have in the third carbon a double bond, which is an ene group. So we have seen all our functional groups, and the parent chain is 5 carbon atom, which would be pentene. So how do we name that? Alphabetically, ene should come before ein. So where is ene located? On the third carbon atom. Okay, so we write 3 pentane 1 ein. Now take note, you may be thinking, why didn't you say 3, 1 pentine? You can discover that you would be confused. Why wouldn't you say that? Because we're just listing what the substituent groups are, and then we add the parent name at the end. Rules have changed. Now, the ein there you're talking about is in the first carbon. It's in the first carbon. So that becomes the parent chain. Well, that's what we calculate the parent chain from. And the substituent is now the N, the double bond. So when we state where the double bond is, we're going to call the triple bond with the parent name. But the parent, if we want to call the triple bond with the parent name, it should be pent1-ine, pentine. So, but there is a double bond in the third carbon, so we have to state that 3-pentene. If there was no ine, if there was no triple bond, it would be 3-pentene or pent3-ene, something like that. But you understand better when we're in class. We'll do a summary of all this, and you will see physically. Can't just let it like that. So we have 3-pentene. Then we state where the triple bond is located. It's located in the first carbon. So one was triple bond called ine. So 1-ine. So we read the formula or the name: 3-pentene 1-ine. Remember, I did not say 3-pentene 1-ine. There is an ine at the end that we want to write. So we have to shorten the ENE and call it N to show that we're going to continue. That's not the end. Remember, we are calling the in before and because alphabetically E should come before Y. Alright. If you also look at the example just below the one we just finished now, that one that is 3,4-dipropyl 1,3-hexadiene 5-ine, you discover it's easy to count that straight chain if you follow those rules. Because if you want to use the branch is to count. You discover none of them have double bond or triple bond. None of them have multiple bonds. So they don't even stand as competitors. They are already gone because you number the straight chain or your parent chain with using the chain that has the highest multiple bonds. So if you want to cut this and branch, you discover you will not yield any results because none of the branches they have multiple bonds. They don't have double bond or triple bond. So the straight chain here has to win. Now in this your straight chain, another thing you will have to consider is which one will give the double bond the lowest number. Because if you want to count from left, triple bond, there's a multiple bond at the first carbon. If you want to count from right, there's also a multiple bond from the first carbon. So you have to choose using the one that gives the double bond the closest chain, and that is the one and numbered 1. So you cannot use this 6 as 1. So you count from 1 and numbered 1, that's right to left. So if you've done that, you number 1, 2, 3, 4, 5, 6 carbon atoms on your straight chain. Having done that, you discover that 6 carbon atoms means what? Hexene. But there is also an alkyne kind there, so it's not going to be hexene alone, hexane and something ine, because there's also triple bond in that structure. Now we're finished with parent name numbering. Now we want to count the substituent groups. Now remember, there's a branch on the third carbon. The third carbon has CH2, CH2, CH3 group linked to it. Remember what we said about alkyl groups. Alkyl groups are derived from removing one hydrogen atom from a corresponding alkane member. So let's look at that branch. How many carbon atoms does that branch have? Starting from the carbon atom after the third carbon, that's the branch. Start counting from CH2, CH2, CH3. Totally, it has 3 carbon atoms. If we look at alkanes, which one should have 3 carbon atoms? Propane, remember prop 3. Propane should have 3 carbon atoms. Now, but if propane has 3 carbon atoms, how many hydrogen atoms should it have? It should be, CN, H2N plus 2. So 2N is 3 times 2, 6, plus 2 is 8. So propane should have C3H8. But since alkyl groups will just lose only one hydrogen, if propane loses one hydrogen, it will not be C3H8 again, it will be C3H7. So now let's count that hydrogen and carbon on that branch and see if it's that member we're talking about. It has 3 carbons, 2 hydrogen plus 2, 4 plus 3, 7. So it has 3 carbon atoms, 7 hydrogen atoms, which means it's just 1 hydrogen short from propane, which makes it an alkyl group. And which alkyl group, since it was propane, is going to be propyl. So that's functional group, that branch there, that alkyl group on the 3rd carbon is propyl. So you can just use something and write somewhere else, okay, that's propyl. So we have identified the functional group on the 3rd chain, that's propyl. Now if we come to the 4th chain, we also have a functional group. What's that? Still count. 3 carbon atoms, how many hydrogen? 2, 4, 5, 6, 7. No, the same thing as the one in the 3rd carbon atom. So that's still propyl, right? Good. So on the 3rd carbon and the 4th carbon, we have propyl groups each. So we write that down. Now, those are all the substituents in that chain, apart from the multiple bonds. So now let's go. We list out the substituents. The 3rd carbon atom had propyl, and the 4th carbon atom had propyl too. We will not say 3 propyl, 4 propyl. That will make this name very long. So we'll just combine them and use di, since it's 2. 3, 4. 3rd carbon and the 4th carbon. 3, 4. What are there on the 3 and 4 carbons? Propyl, but it's 2, so dipropyl. We are finished with the substituents now. Now let's think about the double bond and the triple bond. The double bond is given more priority, so we count that first. Where do you find double bonds? 1st carbon atom, so write 1. And on the 3rd carbon atom also, so we comma 3. Those are all the double bonds. Okay, so now how many carbon atoms are on that parent chain? It's 6, so hexene. All right, so we say 1, 3 hexadiene. We don't say hexadiene now because there's still a function triple bond waiting, so we'll add something. So we say hexadiene. Hexa means that the straight chain has 6 carbon atoms, and it contains 2 in groups, 2 double bonds. That's the di means 2, and where are those 2 double bonds? And the 1 and 3 carbon atoms that we have listed. So 1, 3 hexadiene. Now we did not list the 3 triple bond, so we'll look at it. Where is it? On the 5th carbon atom. Okay, so and that's the only one, triple bond, so we write 5. And what is triple bond called? Ine. If you listen very well, you will see that it's very easy to name it. So if you want to read that, you say 3, 4 dipropyl, 1, 3 hexadiene, 5 ine. If you do that, you discover that it's very easy for you to name these unsaturated hydrocarbons. Just take you more practice, and when we resume fully, we're going to practice very well on this. But I want you to keep doing it until it's very easy for you to practice. Now, preparation of alkenes. Now, the first way to prepare alkenes from this note is from alkyl halides. Remember, halides are halogens, group 7 elements in the periodic table. So from alkyl halides, if you look at that equation down there in number 1, you see the X. Remember, when we're doing functional group, we identify the halide functional group, the halogen functional group, with X, and the X can be chlorine, bromine, iodine, astatine, fluorine, anyhow, all the halogens, any of the halogens. So in that equation, you see X branched from that alkane series, so it becomes an alkyl halide. So that alkyl halide is treated with alcoholic potash and heat, so to produce what's the products there, which has a double bond. So we have created an alkene member. You see the double bond now. So that's the first way. Second way, from alkanols. When alkanols react with concentrated sulfuric acid, H2SO4, it results in the formation of alkenes, because that will eliminate 1 molecule of water. Now, if you look at that equation, now this is what we call dehydration of alcohol. Look at that equation. You see, we had ethanol had that you have two carbon atoms at the center, and oxygen or hydroxyl group, that's alcohol group, branch on that the second carbon atom there. That's ethanol. So if you treat ethanol with concentrated H2SO4, that's sulfuric acid, you will see that just look at that ethanol again. Just look at the ethanol. Don't remove your eye and follow what I'm going to say. If you remove that OH, if you remove the OH and you don't add anything, you see that one bond that is down, that line that goes down from C, will tend to be empty. So what will happen? It will shift and create a double bond with the center, the one that is linked to carbon. And when that happens, it means the hydrogen on the left hand side of the first carbon, the one that this one has been linked to now, will go out. When it goes, so because carbon cannot have more than 4, so when this link, that one goes out. And if that one goes out, now look at that OH that you removed first. If you add this OH with the H again that has gone out here, that's 2H and 1O. What's that? H2O. That's what? Water. So that's what is formed on the right hand side here. You see, the OH leaves and carries one hydrogen with it because of the double bond that has been created, and it now formed H2O on the other side. So what is remaining will have a double bond. That's how to form an alkene member from alkanols. You can also form it from vicinal halides. Remember, whenever you hear halides, we're talking about halogens. Now, vicinal dihalides are halogens with two adjacent carbon atoms attached to two halogens. If you look at that example, you see we have CH2Br linked with CH2Br. You see that Br is on the left hand side of CH2 and also on the right hand side of CH2. So adjacently they are linked together. Thus that's a dihalide. Now you see we use that to produce CH2 and zinc bromide or bromide here. So that CH2 has a double bond. So we've created an alkene member. Now that process is called dehalogenation. Alright, combustion of alkenes. Remember, combustion is burning. I said that alkenes, because they have double bond, they burn with more smoke and more heat, because they have more carbon atoms actually. They burn with more smoke and more heat than the alkenes. So, and we say it's because of the high proportion of carbon in alkenes. But now we remember this, we gave a formula for alkane differently, and there's a formula here for alkenes, but I want you to use the general formula for hydrocarbons that we stated the other time. So if you open back to alkanes, you see a general formula. Open back to combustion of alkanes, you would see a general formula for all hydrocarbons. Alkene is an hydrocarbon, alkane is an hydrocarbon. So let's use that so that we don't forget. But this also can also be used for only alkenes, the one that is in your notes right now. But there is a note there. You can use also the general combustion equation for all hydrocarbons, like the one we used the other way. And if you use that, it still gives you the same result. Now, addition reactions. All unsaturated hydrocarbons, example, alkenes and alkynes, as long as it's not a single bond, they all undergo addition reaction with hydrogen, with halogens, with hydrogen halides, with chlorine and bromine water, with tetraoxosulfate 6 acid, with tetraoxomanganate 7, and air or oxygen. So they undergo addition reaction. Alkenes and alkynes, those multiple bond structures, they undergo addition reaction. Please put that in your head. The alkanes undergo what? Substitution reactions. But the alkenes and alkynes undergo addition reaction. Though as we go on, you'll see that alkynes can also undergo substitution reaction, but it will also undergo addition reaction. But for alkenes, it undergoes addition reaction. So what is addition reaction? Addition reaction involves the direct addition of an attacking reagent across the double or triple bond of an unsaturated compound to yield a saturated product, or at least a product in which the degree of saturation is increased. If you study that structure there, you will understand that better. So what are the uses of alkenes? Ethene, which is the first member of alkene, is used in making plastics and synthetic rubber. When you get to SS3 and you are doing polymerization, you would discover that ethene is very useful in plastics. Number 2, low concentration of ethene are used to hasten the ripening of fruits. That is, ethene is used as artificial fruit ripeners. Use ethene to ripen fruits. Those people that sell fruits in bulk, see in trailers and all those. If you are going to make them ripe so that you use them for your company, juicing companies, maybe fruit juice companies sell orange. They want the orange to get ripe and they want to use it today. You cannot say, let's wait till when the fruits are ripe, we pluck them. They can get them in bulk and then use artificial ripeners. Example, ethene. Low concentration, no. Good. Number 3, ethene is the main source of many organic compounds like ethane, ethanol, and etc. Remember when we did preparation of alkane, we said we can form alkanes from alkenes. So if we use alkene or ethene, you can add hydrogen to hydrogenation process. We can add hydrogen to ethene to form ethane. Remember, so it's also used there. Okay, so we have already discussed how alkynes are the rules for naming alkynes. So let's briefly discuss what an alkyne is. Alkyne has a homologous series. It's a homologous series of unsaturated hydrocarbons with a general formula CnH2n-2. Please take note of all this. Alkane is CnH2n plus 2. Alkene CnH2n, nothing else. Alkyne now CnH2n minus 2. Now, when you have all these in the unsaturated hydrocarbons, the N there must be 2 or greater than 2. Now, each alkyne molecule contains 4 hydrogen atoms less than the corresponding alkane and 2 hydrogen atoms less than the corresponding alkene. Remember the other time we said if you take the first member of alkane, remember C, carbon, has to be bonded with 4. It must bond out its 4 bonds. So in alkane, that's the first member there, methane. You have CH4 because 4 hydrogen just have to come in and bond 1 with the 4 carbon bonds it has. But in alkene, we have double bond. So if 2 carbon atoms use a double bond, they have already on their own used two of their bonds each. So what is left, since 1 carbon has to use only 4, what is left for each of them is 2 other extra bonds. So each carbon atom will have 2 hydrogen and 2 hydrogen on this other side and use the other 2 for the double bond. That's why hydrogen now reduced by 2 and became 4 hydrogens for 2 carbon atoms when it was 4 hydrogen for only 1 carbon atom in alkanes. Now when it comes to alkyne, it has to even further reduce because now 2 carbons, they are using up 3 bonds, 3 of their bonds each to form triple bond. Remember when we said that you just use of their 3 bonds each. So 1 carbon has maximum of 4 bonds to use, and it has used up 3 bonds to create a triple bond each of them. So they are left with 1 each. So how many hydrogens will we be having on each side? 1. So you see that 2 carbons will now be having 2 hydrogens. Methane, that's alkane series, had 1 carbon to 4 hydrogens. Alkene had, that's ethene, had 2 carbons to 4 hydrogen atoms. Now this one has 2 carbons to only 2 hydrogens. So if you relate that properly, you see that an alkyne molecule contains 4 hydrogen atoms less than alkane and then 2 hydrogen atoms less than alkene. And this is because each alkyne molecule contains a carbon-carbon triple bond, like I've explained, where 2 carbon atoms are bonded to each other by the sharing of 3 pairs of electrons. Thus, the alkynes show a higher degree of unsaturation. So this one is more unsaturated than the alkene, but they are all unsaturated compounds except alkane. Hence, they are chemically more reactive than the alkanes and alkenes. The higher the amount of unsaturation, the higher the chemical reactivity. That's what you should know. Now, if you look at that table, the same thing we did for alkane and alkenes. You will discover first member ethyne, second propyne, third butane, pentyne, hexyne. Remember this prop, they are all for the carbon atoms, the number of carbon atoms. It doesn't concern itself if it's the first member. First member is you are first member depending on the number of carbon atoms you have. So the least number of carbon atoms is the first member. One bigger than that has to be second number. So that's how it goes. It's not like the one that has more carbon atoms is the first member, since it's the this one, the one that has smallest, the lowest carbon atom is the first member. So in alkyne series and the alkene series, you don't have methine, you don't have methane, because meth means one carbon atom, and one carbon atom is not possible for unsaturated compounds. That's compounds that have double bond and triple bond. So 2 carbon atoms is the lowest they can have. So that's mean 2. So that becomes the first member, ethyne, propyne. If you follow up, you study the structure and the formula, and you will see how it is. Now, how do we prepare alkynes? Since we have already discussed how we name them under alkenes, how do we prepare alkynes? Alkynes can be prepared in a number of ways. Number 1, from the dehydrohalogenation of alkyl halides. Number 2, from vicinal dihalides from calcium carbide. Those 3 ways we can use them. We've already mentioned how vicinal dihalides are there. We have also did halogenation of alkyl halides, so that's why I did not state them out well. But look at this. In the laboratory, alkynes are prepared by the action of cold water on calcium carbide. See, now I'm saying action of cold water on calcium carbide. What action is this? Addition. Adding cold water to calcium carbide, that's the action. Remember, we said that alkenes and alkynes go through addition reaction, and we have defined, you have done what addition reaction is. We defined it. So the action in the laboratory is addition, adding cold water to calcium carbide in the laboratory to produce to prepare an alkyne. Now, for large-scale production of alkyne, calcium carbide is made to react with water. That's what we mean. I'm just explaining. It is prepared by heating quicklime calcium, in the presence of coke. Remember coke when we're doing carbon. Quicklime is obtained by introducing limestone to heat. The reactions for the preparation of ethyne is what we have as the formula. CaCO3 produces CaO, calcium oxide, plus CO2, carbon dioxide. Then you see from there, we'll react the CaO produced in that first equation with 3 moles of carbon, and then you have CaC2 plus CO. So now you react the CaC2 produced from the second equation with 2 molecules of water, and then you have your ethyne. So that's how to prepare ethyne, or preparation of an alkyne. Ethyne is an alkyne. So we just use that. You can also produce others using the same method. Remember. Now, combustion of alkynes. Alkynes burn in air to give a very smoky and luminous flame due to the very high percentage of biomass, about 92% of carbon in them. So remember, alkanes are stable. They burn because they have carbon in them. They burn. But now, the number of carbon in alkenes are more than that of alkanes. So alkenes are going to burn brighter. But not brighter, burn more smoky. So it has more carbon in it. But alkynes have even more carbon, than alkenes. So it's going to burn even more smoky and luminous. So that's why alkynes burn. And the percentage of carbon to hydrogen is 92 to 8 in alkynes. So Alright, alkenes and alkynes burn with yellow flames, while alkanes burn with blue flames. Here I underline that, so take it very seriously. Alkenes and alkynes burn with yellow flames, so those unsaturated hydrocarbons burn with yellow flames, while alkanes, the saturated one, burns with blue flames. Now take note of this very important aspect. Ethane burns with very large amounts of heat. It's about 30,000 or 3,000 degrees Celsius of heat produced when ethane is burned as an alkyne. Now, this hot flame is used in oxyethene touch. You call it oxyacetylene touch also. It's the same thing, oxyethene touch or oxyacetylene touch, which is used in welding and cutting metal scraps. If you've seen welders, if you've gone to welder shops, you'll see some cylinders, tall cylinders, gas cylinders. You'll be wondering what are they using it for. That's oxyethylene gas inside there. So by the time they press the nozzle of the nozzle, and the gas comes out through the nozzle, light it up, and then the heat produced there can be used to cut metal. It's as hot as that. So that's a very useful that's a very good way of using an alkyne, ethane. Okay, now the formation for combustion of alkynes is that is in your notes, but remember, I always want you to use the general equation for the combustion of hydrocarbons to calculate it, but you can also use this and you get your same results. Okay, now addition and substitution reactions. Remember I said the other time that as you move on, you discover that alkynes also go through substitution reaction, not just addition like the alkene goes through only addition. So alkynes readily form addition reactions with hydrogen, halogens, hydrogen halides, water, and tetraoxomanganate 7. But now all alkynes with a triple bond at the end of their carbon chain, like you see example I wrote there, undergo substitution reaction. So you can have an alkyne, the ones that maybe the triple bond, it's triple bond that tells you that it's an alkyne. So if it's a triple bond and it's if the triple bond is at the center of the chain, or maybe somewhere inside the chain, but not at the end last carbon, the boundary carbon, the two boundary, not there, then you can use addition reaction. But if the triple bonds are at the ends of the carbon, then it can also use substitution reaction. Alright, polymerization of alkynes. Ethane polymerizes to form the aromatic hydrocarbon benzene. So we are getting down to benzene now. So you can use ethane to produce benzene through polymerization. Now, how do you test for unsaturation? That's how do you test for compounds that are unsaturated? Unsaturated compounds are best recognized by the addition reactions. Remember, alkenes and alkynes, they undergo addition reactions. So if in your reactions it's an addition reaction that gave your result, then that shows you that was an unsaturated compound. The most convenient test is a reaction with bromine. That's bromine water. Bromine water is reddish brown. So what happens when unsaturated compounds are being added to bromine water? Take for instance an alkene or an alkyne. Example of alkene is ethene. So if you carry ethene and add, remember I'm saying add now because it's addition reaction you use. So if you add the ethene to bromine water, which is reddish brown, it changes the color of the bromine water from reddish brown to a colorless liquid. So the reddish brown color will disappear and the liquid becomes clear, colorless. That shows you that compound you added to that bromine water is an unsaturated compound. Alright, so that's a very quick way of testing for unsaturation. Now, what do you use alkynes for? You see in your notes, you see the ethane is mixed with oxygen to produce very hot flame. That's oxyethylene flame that we explained there. And ethane is used in dry cleaning for dissolving grease. That's self-explanatory. Let's rush into aromatic hydrocarbons. I said the other time that aromatic compounds are benzene and compounds that resemble benzene. As we move forward, you see those compounds that resemble benzene. That's benzene type compounds. You'll see them. Now, benzene is obtained from destructive distillation of coal. Remember destructive distillation? When you are heating coal in absence of air, good, limited amount of air. So that's destructive distillation. So coal was destructively distilled, then benzene was produced. So it can also be obtained by the polymerization of alkynes. Remember, we just said not long ago that in the polymerization of alkynes that ethane polymerizes to form aromatic hydrocarbon benzene. So we can get benzene out those two ways. Now, what's the structure of benzene? In 1865, Kekul, now some people can call it Kekule. Some people can even call it Kekula. Anyhow you call it, but at least you know it's not English. So you can, as long as you know the spelling and you know the year he proposed this, and then you know what he said, you're good to go. Spell it well, but you may not pronounce it well, but if you can pronounce it well, fine. But okay. In 1865, Kekul suggested that since the formula of benzene is C6H6, then the most logical structure would be for the 6 carbon atoms to form a ring with the 3 alternate carbon double bond in the ring. So if you see that example, that diagram I drew, the one by your left, you'll see that I spread out that 6 carbon atoms to form a ring. That's they almost like a circle, they join. That's what we call rings in hydrocarbons. So when the 6 carbon came in, each carbon is linked with 1 hydrogen. So if you count the number of carbon, C is 6. Count the number of hydrogen, H is 6. So we said that, they said that the formula, since the formula is C6H6, and so we can place it this way. That was good though. But take note, you will see in that diagram, you have double bond, single bond, double bond, single bond, double bond, single bond. You discover that. You see double bond here, and the next bond will not be double. Go to the next one, it will be double, next one single, next one double. That's how the structure looks like. But that double bond you are seeing there is not compulsory that it must be on the carbon that we are seeing it now. Where you are seeing single bond, you can also move the double bond there, but when you move it there, the one you have moved the double bond from will become single now. So because of this, that's trying to say that the double bond is not fixed. It can move to the next carbon. So it's not a fixed position that the double bond is there. So because of that, you look at see the diagram on your right hand side. You see that the double bond, I shifted it to the next carbon. So the other one that was double on the other diagram became single. So this is showing that the double bond they are alternating, they are moving. It's not it must not be on that carbon. Yeah, you put it in the first place. So it's alternating. So if this is alternating, how can we come out with a plain one diagram to show that to show a consistent way to have a consistent way of showing the double bonds? So the notes behind now. Since the double bond does not have a fixed point in the benzene ring, the structure of benzene was later modified to have an inscribed circle. Now you see down there, you see that the diagram that has a circle inside. Now the inscribed circle indicates that the double bonds are shifting at all times. This means that the 6 electrons involved in the double bonds are moving around the 6 carbon atoms in benzene. So you see with the diagram now, you will not really tell which carbon atom is the double bond on. So that circle inside just means that the double bonds, they are moving. So you understand that now. So the 6 corners, 6 points of that diagram, the 6 corners of the structure represented in that this diagram are the 6 carbon atoms. So these are the 6 carbon atoms. Since we've drawn it this way, we don't need to write out this. When you start doing isomerism and you see, or maybe you will not do it right now, maybe in your university level, there are some ways you will draw hydrocarbons. You will not need to identify which one is C. All the sharp points are the C. And you bear in mind that all these tips, the point there, they are linked with hydrogen, but they are not shown there, but you have it in mind because you know the diagram above shows you. So the 6 points, the 6 edges there, the 6 they are the carbon, where the carbon meets. but then have it in mind that each carbon is linked with one hydrogen, and the circle inside means that the double bond is always moving. Now, what are these benzene type compounds? So we said that aromatic compounds are benzene and benzene type compounds, that compounds that resemble benzene in chemical behavior. So what are these benzene type compounds? So some common aromatic compounds are phenol, toluene, xylene, and then others include pyrrole, furan, thiophene, etc. Now, in O-level chemistry, that's SS1 to 3 chemistry is O-level chemistry. In O-level chemistry, you are not expected to know so much about aromatic compounds. Not necessarily, but it's not a crime to know. So you see those diagrams I drew there, diagram for phenol, toluene, xylene, pyrrole, furan, thiophene. Now, you are expected to be able to see the diagram and know which one is which. So it's not very hard for you to quote these 4 or these 6 diagrams. Just put it in your memory that, okay, phenol has hydroxyl group, alcohol group as its functional group, okay. Toluene has methyl group, CH3, as its functional group, okay, just that. And xylene has 2 methyl groups, CH3 2 times, so, okay. Then pyrrole has a nitrogen group, nitride. Furan has oxygen. Thiophene has sulfur. But just look at the structure and the double bonds where they are placed. That sometimes in WIAC it comes out in exams, and then you just draw this and say what compound is this. And they put in the options: phenol, toluene, xylene, and they were drawing furan, and then you choose furan. So that's how to use that for your consumption for exams. Now, physical properties of benzene. Benzene is a colorless liquid with a sweet smell. Remember, sweet smell, aromatic compound has sweet smell because aroma. Alright, benzene is a colorless liquid with a sweet smell. It is insoluble in water, means it does not dissolve in water. It has a boiling point of 80 degrees Celsius, mean water is more dense. So, chemical properties: benzene undergoes substitution reactions and addition reactions. That's just like the alkynes. Not all alkynes. The alkynes that have triple bond at the edges will undergo substitution reaction, where other alkynes undergo addition reaction. But benzene undergoes substitution and addition reactions. Uses of benzene: benzene can be converted to styrene. Now, styrene is used in the manufacture of synthetic fibers, just like nylon. Styrene can be used for so. Benzene is an important source of chemicals which are used as pesticides and detergents. So you see how chemistry is life. So toluene is used in making explosives. Remember the structure of toluene, we do that, okay? So now phenol is used as a disinfectant and as a raw material for making plastics, which is also, toluene is a derivative of benzene. And phenol also is a derivative of benzene. So number 3 is just talking about all the some derivatives of benzene, how they are used. So toluene is used in making explosives, while phenol is used as a disinfectant and also raw material for making plastics as polymerization. Aniline and aniline type compounds that resemble aniline are used for making dyes and drugs. So pharmacists, they will use that also. All right, so that's benzene, or that is alkene, alkyne, and then aromatic compounds. In our next class, we are going to do, still on this topic, isomerism, and then we conclude with alkanols. We'll do isomerism, and you'll see how the structures can be rearranged, and then we get to finally alkanols to conclude this topic. All right, so until then, have a nice day.